everyone. The topic of our poster is the promise of hydrogen energy. We think our topic is important because mankind is using more than 1 million terajoules energy every day, and the world's energy consumption is also expected to have increased by 50% by 2040. Now, hydrogen fuel has immense potential. Its energy efficiency of around 50 to 75% is more than twice in that of most other fuel sources. However, it has several pitfalls and hurdles, which brings us to our research question. How can we overcome the hurdles of making hydrogen fuel more efficient and reliable? Now, the different variables that we target are efficiency, safety, and optimization. And in the future, we aim to look at the cost effectiveness.
So our role is conducting a meta-analysis for our research to figure out how to make hydrogen more efficient and safer. We compare the energy content of gasoline, diesel, hydrogen, and electricity in normal conditions, which is at 1 atm and 293 Kelvin, to measure the efficiency of hydrogen compared to other fuels used for automobiles.
We also use the ideal gas law to estimate how many moles of gas can be carried in a tank when you keep the pressure and volume constant when manipulating the temperature. So we're using the ideal gas law to do this because hydrogen is a small molecule, which means it doesn't take up a lot of volume, and it has nonpolar intermolecular forces, which means it doesn't really attract to itself, which means that the ideal gas law can be applied. And through doing this, we got, as you can see, stuff in table 2.
Our first figure is the energy content in normal condition of these four fuels. Different fuels have different levels of energy content, which can be measured in terms of equivalent energy raised through combustion. The higher the energy content, the higher the fuel quality, which is inversely proportional to its chemical complexity. As we can see in the figure, high quality fuels are gases while low quality fuels are solids with liquids in between. The highest energy content fuel is hydrogen, which is also the simplest chemical component in existence. Meanwhile, gasoline, which is derived from refining crude oil, contains approximately the same amount of energy as diesel.
So looking at figure 2, it's really important to note the exponentiality of this temperature and moles of gas relationship at like this constant pressure and volume, which can be manipulated because really the lower the temperature you go, really just so many more moles can be packed in. And there's really no exceptions to this because it has to follow the ideal gas law. And through the different colors on the graph, it's important to see that you can, if you increase the pressure and volume, you can really pack more moles of gas in at a given temperature, but it's also like more dangerous because it's more likely at higher pressures that the hydrogen can like explode. So it's all about like a risk benefit analysis, seeing is it worth it to like increase the pressure to pack in more moles of gas, but there's a higher chance that everything just explodes.
So regarding our group's further analysis, also hydrogen has higher energy content than most other fuels. As we can see in the figure, their gaseous form creates storage difficulties. Moreover, hydrogen must be synthesized, which requires a lot of energy. To compare with other fuels, with a conversion rate of 100%, it would require 100 hours to capture the solar energy equivalent of 1 kilogram of gasoline on the surface of 1 square meter. On the other hand, one of the most efficient energy storage devices, which is electricity, where we use lithium battery for the comparison, can only hold about the equivalent of 0.5 megajoules per kilogram.
So looking back at figure 2, it's important to note that like, oh, you can't just decrease the temperature like almost to pretty much 0 because it costs energy to decrease that temperature. It's like 4 times more expensive to cool than to heat. So what we recommend is keeping the gas, the hydrogen that you're packing at room temperature or cooler, depending on how much money you have available to use to put that energy in to decrease the temperature and how much is like economically feasible so that you're not losing money and putting more energy in than you're getting out.
To conclude, we can see that hydrogen is more efficient than other fuels, but it's also expensive to store and to keep it safe. We also wanted to target into the factor of cost for this research, but we couldn't do so because different states and different countries have different incentives towards hydrogen fuel. For example, even the US, different states have different outlooks, with California having a lot of incentives while others having less to none. To explain more upon the same, we have created a website which is listed in the footer of this poster as well as the description. We have also explained more upon the efficiency of hydrogen in the same. Thank you.